Sisi.
Oh, okay. Thank you for the nice introduction. Okay, so today I'm going to talk about error-corrected quantum metrology. So first, let's take a look at quantum metrology. So quantum metrology is the study of measurement and estimation in quantum systems. So it has a lot of applications in different experimental platforms. For example, like in optical interferometry, we can use metrology to estimate the gravitational wave. And also like in atomic clock, we can estimate the frequency of the atomic clock. And also like in nitrogen vacancy centers, we can estimate the magnetic field and electronic field. So, and so on. So, and my talk is going to focus on the theoretical aspect of quantum metrology, basically the underlying estimation model of these situations. So before we take a look at quantum metrology, let's first take a look at classical estimation. So in classical estimation, suppose we have some unknown parameter omega we want to estimate. And what usually happens is that we, instead of having the exact value of omega, we have a probability distribution. And X here is the measurement outcome. And then we try to estimate the value of omega using some estimator omega hat. And we can define the estimation precision to be the variance of this, the square root of the variance of this omega hat. And moreover, for unbiased estimators, we have this Cramer bound, basically saying that the delta omega is lower bounded by 1 over the square root of n times f, where n is the number of experiments and f is the fission information. So it is a function of this probability distribution. And we can somehow think of it as a distance measure between like the probability distribution at omega and the probability distribution at omega plus d omega. So more importantly, the bound is searchable asymptotically using maximum likelihood estimator. So basically, when this number of experiments is infinitely large, this bound is searchable. So that's why fission information is an important quantity to quantify like how precise an estimate parameter could be estimated. So here is a precise definition of fission information. And to give you an example, we could consider Bernoulli distribution. Basically, we have two outcomes. One is x equal to 0, and the other one is x equal to 1. So basically, if omega is simply the probability of getting 0, then we can calculate the fission information, and it will give you 1 over omega times 1 minus omega. So basically, when this coin is almost unbiased, it is the most difficult to estimate omega. So yeah, so now let's generalize this to the quantum case. So here is the again the definition of classical fission information, and we can write it in certain ways. So it could be the expectation value of this L square, where L is the logarithmic derivative defined by this formula. So we could take the logarithmic of this P function and then take the derivative, and it will allow us to calculate this L. And we can generalize these concepts to the quantum case by assuming the probability distribution is a density matrix, and this logarithmic derivative becomes a Hermitian operator. So we get our quantum analog. The quantum fission information is the expectation value of this L square. And L is so-called symmetric logarithmic derivative defined by this formula. So basically, we could solve L from this formula and then calculate the quantum fission information. And again, we have the quantum estimation theory. So here we have some unknown parameter omega, and it is encoded in some density matrix rho omega. And what people do is they perform some quantum measurement on it and give us a probability distribution, and then we estimate omega from the probability distribution. So the quantum Cramer bound says that delta omega is lower bounded by 1 over square root of n times f. And here f is the quantum phase emission, and it is a function of this density matrix. Moreover, one definition of the quantum fission information is that it is the maximum of all the classical fission information over all possible POVM. So, and also fission information is somehow like related to the distance between rho omega and rho omega plus d omega. And more importantly, we can see that the quantum Kramer bond is also saturable asymptotically. So basically, we just pick the optimal measurement from here, and then we use the maximum likelihood estimator. So now let's take a look at a few examples of quantum fission information. So the first example is pure state. So here the quantum state is just pure state, and with some Hamiltonian evolution where the Hamiltonian is equal to omega times h, and t is the probing time. So then the fission information is basically just going to be 4 times t squared times delta h squared. So basically this is the variance of h per psi. And we can also see that the fission information is proportional to t squared, and that is an important feature I need you to remember. And one simple example is when the Hamiltonian is Pauli Z matrix over 2. And in that case, we can pick the optimal initial state, which maximizes this variance to be the plus state, basically the 0 state plus 1 state over 2, the square root of 2. So this is pure state. But what happens if we have, like, for example, dephasing noise? So instead of only having this Hamiltonian evolution, we can also have this dephasing term, dissipative term in the master equation. So here gamma is the noise rate, and again, if the input state is again this plus state, in the noiseless case, we already know that the fission information is going to be t squared. But in the noisy case, the fission information is going to be t squared with some exponentially decaying term. So we can plot, sort of plot this p, this rho t projected onto the initial state, and we can see that in the noiseless case, the curve is going to oscillate with some frequency proportional to omega. But in the noisy case, instead of only have this oscillation, we also have a exponentially decaying envelope. So that explains why we have this exponentially decaying term in the fission information. And in that case, if the optimal strategy is to measure and renew the qubit every constant time. So in the end, we can only get fission information proportional to t. So that's one qubit case, and we can also have n qubit case. For example, if the input state is GHZ state, then in the noiseless case, we could have fission information proportional to n squared. So basically, the first fission information is going to be n squared times t squared. So that's nice. But in the noisy case, we would have fission information to be n squared t squared plus with some exponentially decaying term. And moreover, we can see that the decaying constant is actually n times larger than previously. So again, we could make the same plot. We could see that the oscillation is like n times faster, but the decaying is also n times faster. So and in the end, if we just calculate the average QFI over time, we would get something which is proportional to n. And moreover, it is exactly the same as if we use the product state. So basically, in this asymptotic sense, there is no point in using this GHZ state compared to this plus state, product state of this plus state. So to summarize, in quantum metrology, we care about the resource, which is the number of channels we use or the probing time. So there are two types of estimation precision limit. The first one is the Heisenberg limit, where QFI is proportional to n squared or t squared, and that is the ultimate estimation limit allowed by quantum mechanics. And the second case is the standard quantum limit, describing the situation where QFI is proportional to n or proportional to t. And it is somehow like the classical limit because we don't need to maintain the coherence for a sufficiently long time, or we don't need to build an entangled state to get to this limit. So that's the two limit. And basically the one important subject in quantum metrology is to study like when can we get a Heisenberg limit. So in general, we could consider the estimation of a quantum channel. So suppose we have some quantum channel described by this epsilon omega, and we want to estimate this omega. And we could have like many different situations. For example, if we have the unitary channel, then we want to estimate the strength of this Hamiltonian. Or if we could have this Hamiltonian estimation on the noise. So basically, again, we have this Hamiltonian evolution, but we also have some noise acting after this Hamiltonian evolution. And like in general, we could consider an arbitrary quantum channel where the cross operator is a function of this omega. So, and what are the estimation strategies in this case? So the first one is called the parallel strategy. So basically, we assume we can prepare a initial state entangled over n different probes and also a bunch of ancillas. And then the channel acting on each of the probe in parallel. And then we can do a final measurement, which could also be an entangled measurement over this whole state. And then we ask what is the Fisher information, a quantum Fisher information of this final state. So that's parallel strategy. And a more general strategy is called sequential strategy. Basically, we assume the quantum channel could be acting on each other with some quantum controls in between. So basically, it is more general than the parallel strategy because, for example, we could assume that this control is just a swap gate, and then we reduce back to this parallel strategy. So, and now we also assume we have like n quantum channels acting on a single probe, but with quantum control in between. So we also want to optimize the Fisher information in this case. So now the Fisher we care about the scaling of the Fisher information with respect to the number of channels we use. We could also consider the other type, which is the situation where Fisher information has some relation with the probing time t. So in that case, we can just divide the whole quantum channel up into like t over dt different small quantum channels, and then we just analyze using the sequential strategy on the previous slide. And one example would be we have this master equation, and this is just the first order evolution of this whole system. And for example, we want to estimate the strength of the Hamiltonian in this master equation. So we could also analyze that using the strategy on the previous slide. So okay, so now we have two important questions we'd like to answer. The first one is the HL vs SQL problem. So basically, given an arbitrary quantum channel, is it possible to achieve the Heisenberg limit with respect to the number of channels using parallel or sequential strategies? So that's one important question we'd like to address. And the second question is, even if we already know what is the scaling, then what is the optimal QFI coefficient? So basically, would have two different coefficients we'd like to study. One is the QFI over n squared, taking the limit where n goes to infinity, and the other one is the linear coefficient. So basically, we'd like to ask what is the optimal QFI coefficients in the parallel or sequential strategies. Okay, so to answer this question, we have to approach it in two different directions. The first one is we want to derive some upper bound of the QFI, and the second one is some lower bound. And basically, in the end, one could show that the lower bound matches the upper bound in some situations, and then the problem is going to be solved. So I'm going to first introduce a little bit about the upper bound, and then mostly focus on the lower bound case where error correction is used. So the first one is the upper bound. I'd like to introduce this channel extension method. And yeah, the second one is related to quantum error correction. So, and we can also use these two methods to derive some useful information in terms of HL coefficient and SQL coefficient. So the study of channel expansion method is like initiated in like 2008 and generalized a lot during in these papers. So what is that channel extension method? Basically, we first study the quantum fission information of a single quantum channel. So suppose we have a single quantum channel, and we also assume we have some ancilla here, and we want to optimize the fission information given a single quantum channel. And that is a relatively easier task. So basically what we can do is we utilize the purification-based definition of the QFI. Basically, suppose we have some quantum state rho omega, and then the QFI could be just the minimization of this quantity over all possible purification of this rho. And then if we just use this definition, and then we just plug in the cross operator of this quantum channel, and it is easy to get to this final expression of the single channel quantum fission information. And so basically we can see that it is a, so the exact expression is not important, but basically we can see that it is a quantity that is a function of the cross operator itself and the derivative of this cross operator. So this dot here basically means the derivative with respect to omega. And this H here is just an arbitrary Hermitian matrix that we are minimizing over. So, and here, this means the operator norm. And one can also show that this is efficiently computable using semi-definite programming. So this is for a single quantum channel, and we could just generalize that. Basically, by plotting, okay.
Real quick, does this alpha, does it have any connections to the Buras distance?
Yeah, actually, I'm not sure. So do you mean like the Buras distance between like two quantum channels?
No, I mean, well, I guess, yeah, I guess I initially wanted to ask about states, but maybe what you're saying makes more sense.
Yeah, I think maybe its connection with Buras distance is exactly the connection of the fission information with Buras distance, which basically is like the fission information is basically the second order derivative of the Buras distance. So that's the connection, I guess. So you can also use a quantum channel, I guess. Yeah, I'm not entirely sure. Yeah. Okay, so yeah, so now we can just plug in the cross operator for the n copies of quantum channel, and we could get the fission information of this parallel strategy. And we would have two different terms. The first term is linear, and the second term is quadratics. So basically, instead of having this alpha operator, we could also have this beta operator, and they are all Hermitian operators. And in the sequential strategy case, we could have similar upper bound, but a little bit different. So the linear part is the same, but the quadratic part is going to be slightly different. So basically we would have the norm of beta times something which is larger than in the parallel case. But more importantly, we can see that the Heisenberg limit is not achievable if there exists an H such that beta is 0. So if beta is 0, then the quadratic part goes away and we could only have the linear term. So, and then we can only reach the standard quantum limit. And some example would be depolarizing noise with arbitrary Hamiltonian evolution, and also like Pauli Z signal with dephasing noise. So basically, there are many typical situations where the Heisenberg limit is not achievable. So that's the upper bound part. And now I'm going to move to the lower bound part. And I'm going to first tell you the conclusion in terms of HL vs SQL. So the conclusion is that there exists some condition, linear algebraic condition, basically, which help us determine whether or not we can achieve this Heisenberg limit. And the condition goes like this. So we could define, for an arbitrary quantum channel, we could define its Hamiltonian by this quantity. And we could also define the crossband by this quantity. So, so here, this double H basically means we're only considering the span of Hermitian matrix. And then if this Hamiltonian is not in this crossband, it is possible to achieve the Heisenberg limit. But if Hamiltonian is in the crossband, it is not possible. So it is a necessary and sufficient condition. And I want to remark here that the reason I'm defining this quantity to be the Hamiltonian of a quantum channel is because if we have a unitary channel and some like arbitrary noise acting after this unitary channel, and we just calculate this quantity, it will give us the Hamiltonian of this unitary channel. So that's justify the name of this quantity, why we call this a Hamiltonian. And there's an easy way to, I'm going to give you a simple example of this case. So first, suppose we have some Hamiltonian, which is Pauli-Z matrix, and then we only consider the bit flip noise. In that case, it is easy to say that the Hamiltonian is not in the crossband, because the crossband is just the span of identity and X, and clearly H is not inside S. So it is possible to achieve the Heisenberg limit. And some example would be, and here is a exact code that is discovered. So basically, we could just use this repetition code. So we have 0, 0, or 1, 1 as the 0 logical state or the 1 logical state. And then after an error happens, the parity is going to change. And so the recovery map is very simple. We can just like compute the parity of this quantum state and then flip the probe according to the state on the ancilla. So using this error correction strategy, one can show that basically the Fisher information is going to be exactly the same as in the case where we don't have any noise. So that's an example where the Heisenberg limit is achievable. And more generally, we could consider like the general error correction criterion. So basically, we know that given a quantum channel with cross operator K, there exists an error correcting code if and only if this Kniaev-Lamb condition is satisfied. So basically, P is a projection onto the code space, and K is just the cross operator. So if this condition is satisfied, then it is possible to find a recovery channel, which is the inverse of this noisy channel inside the code space. And in terms of parameter estimation, we could consider the situation where when omega is 0, we have this basically the noisy channel is the one we consider on the previous slide. But when omega is slightly different from 0, the evolution is going to be a effective unitary quantum channel, basically a unitary channel in the logical subspace. And then in that case, one can show that one needs to satisfy the two conditions in order to perform error corrected sensing. So basically, the first condition is exactly the same as the Kniaev-Lamb condition on the previous slide. And the second one is that the signal has to be not proportional to identity. So the signal has to be non-trivial. So in that case, one can see that when the Hamiltonian is inside the crossband, these two conditions cannot be satisfied simultaneously. So that's one explanation that we cannot get to the Heisenberg limit. So okay, so now I'm going to give you a little bit introduction of like how to achieve the Heisenberg limit when these two conditions is satisfied. So basically, when the Hamiltonian is not in the crossband, we could decompose it into two components. The first one is something which is inside the crossband, and the second one is something which is perpendicular to the crossband. And then in that case, the perpendicular part could be decomposed into the difference between two positive matrix. And if we just rescale it a little bit, it could be a difference between two density matrix. And then we can just use this density matrix to define the code space. So the code is again a bipartite state between the original state and also the ancilla. So then we can just use this two density matrix to define this code space. And it is a two-dimensional code, and which also satisfy these two conditions after you like plug it into these formulas. And then we can just use the general logical GHZ states to recover the Heisenberg limit. So that's how we show that it is possible to attain the Heisenberg limit when the Hamiltonian is not in the crossband. And now I'm going to talk a little bit about how to get to the optimal HL coefficient.
Can I think of this thing as like just you trying to find the states that maximize the variance of H perp?
Yeah, exactly. I think that's basically what I show on the next slide. So yeah. Okay. So first, let's define the HL coefficient. I think I already defined it on the previous slide, but basically it is the Fisher information of n copies of quantum channel divided by n squared, and taking the limit of n goes to infinity. So, and the conclusion is that when the Hamiltonian is not in the crossband, then one can show that this thing is equal to this quantity. So yeah, and we can sort of view this quantity as some kind of distance between the Hamiltonian and the crossband. So if some of you have some good memory, you would remember that the quadratic term would have some coefficient, which is the norm of beta squared. So basically, what have left to be proven is that how to attain this quantity asymptotically, and that again uses the QEC protocol I mentioned on the previous slide. So basically, in that case, the Fisher information is going to be the coefficient of Fisher information is going to be proportional to the trace of this quantity times h square, and in order to satisfy the error correction criterion, one need to satisfy the trace of this C tilde times S is equal to 0. So basically, if this condition is satisfied, that means the error correction condition is also satisfied. So that's the error correction condition, and we all want to maximize the signal in this case. And then one can show that the optimal quantity is exactly 4 times n squared times the distance between H and S. So basically, one can see that it is exactly equal to the one, the upper bound we wrote down on the previous slide. So basically, that shows that just by using this two-dimensional encoding strategy, one can attain this HL coefficient upper bound. So yeah, so basically, not only can we achieve the Heisenberg limit, we can also attain the optimal coefficient using quantum error correction protocols. Okay, so now I'm going to move to how to attain the optimal SQL coefficient. And that is a bit more complicated than the HL case. So first, let's take a look at the conclusion. So again, the definition of the optimal, the definition of the asymptotic SQL coefficient is the ratio between the quantum Fisher information of n copies divided by n. So, and the conclusion is that when the Hamiltonian is inside the crossband, the coefficient for the parallel strategy is going to be the same as the coefficient for the sequential strategy. And moreover, they are equal to this quantity. So, and it is basically the norm of this alpha operator minimized under the condition that beta is 0. So again, we could take a look at the previous upper bound derived using the channel extension method. So the upper bound basically says that we have some linear coefficient, which is 4 times the norm of alpha. And we also have some quadratic part, and we want that to be 0. So basically, if we can find some h such that beta is 0, then we're just going to minimize this upper bound, this linear coefficient over all possible h such that beta is 0. And that would going to be the upper bound of this SQL coefficient. And then in order to show that this bound is this is actually an equal sign here, one need to show that this coefficient is achievable, and one need to use the approximate quantum error correction protocol. So the reason that we are using approximate quantum error correction protocol is because if we use exact quantum error correction, then basically if we correct all the noise, then the signal is also going to be corrected. So in that case, we don't get any useful signal at all. So that's why we need to use approximate quantum error correction protocol. So the strategy basically goes like this. We first consider the special case where the quantum channel is a dephasing channel. So by dephasing channel, we don't mean like the traditional dephasing channel, but we mean a situation where basically we have a quantum channel which goes like this. So we have only 1 qubit, but the amplitude of this off-diagonal term is going to be Cauchy times the original amplitude. So and Cauchy is not just a real number. It could be an arbitrary complex number. And when the norm of Cauchy is 1, we have a unitary channel. Basically, in that case, we have the unitary evolution with respect to the Pauli signal. And then in that case, which we have already known is that the Heisenberg limit is actually achievable because we just have a unitary channel. And the Heisenberg limit is achievable, and we can just use the logical GHDC to achieve that. But the more interesting part is about the situation where the norm of Cauchy is, the absolute value of Cauchy is smaller than 1. And in that case, one can show that the upper bound of the norm of the upper bound of the Fisher information is going to be something like this. So basically we have some 1 over the absolute value of Cauchy square in the denominator. So, and we show in this paper that using some logical mean squeeze state, it is possible to achieve this upper bound. So basically we prove that the SQL coefficient is equal to this quantity for dephasing channels. So that's only for dephasing channels, but what about general quantum channels? The strategy is to just reduce the every general quantum channel to dephasing channels. So basically, we assume there is some special type of 2-dimensional encoding, which makes every channel goes to which reduces every quantum channel to dephasing channel. And the trick is that we assume the ancillary space is like 2 times larger than the system subspace. So basically, A1 is the same as S, where S is the system and A1 is just the first register of the ancillary space. And we also assume an additional register, which is A2, and we assume that it is 0 for the logical 0 state and it is 1 for the logical 1 state. And we can also do the same trick for the decoding channel. Basically, everything that starts with 0 goes back to 0, and everything that starts with 1 goes back to 1. So by assuming this structure of the encoding and decoding channel, we can show that this whole quantum channel is exactly a logical dephasing channel. And then in that case, we could just optimize the Fisher information of this logical dephasing channel over all possible encoding and recovery channel. And that would give us the optimal SQL coefficient. So that's the code optimization. So now let's take a look at one example, which is the case where the Hamiltonian is inside the crossband. So here we assume the quantum channel is we have first this Hamiltonian evolution with respect to this Pauli signal, and then we have some amplitude damping noise defined by these two cross operators. So basically one has some, basically one could be flipped back to 0 with some noise rate P. And then in that case, one can show that the crossband is exactly just the entire Hermitian matrix span of 2x2 Hermitian matrix. And that's and Hamiltonian is exactly inside this crossband based on the definition. And in that case, one can compute the optimal SQL coefficient. It is going to be this. So one can see that this quantity is actually just have the scaling of 1 over p when p is very small. So basically, it explains the transition from SQL, from HL to SQL. So basically, when p is going to be very small, this SQL coefficient is going to be very large. And then when p is 0, one goes back to the Heisenberg limit. So that explains why we have this 1 over p scaling here. And we can also solve a near optimal code from the strategy I introduced in the previously. So for the amplitude damping channel, we need a 2-qubit ancillary system. So and then this is just the form of this code, and we have like two small parameters. So one, the delta and epsilon, and they are both very small, and epsilon is even smaller than this delta. And one can plot the Fisher information of this code. So the Fisher information of this code basically goes like this. So when delta is very small, when epsilon goes to 0, we achieve this optimal SQL coefficient. But when epsilon is slightly larger, so basically, even if epsilon is like 0.5 delta, we also get very close to this. We also get very close to this Fisher information, optimal Fisher information when delta is very small. So that's basically the structure of the near optimal code that is solved by the strategy on the previously. Okay, so
just quick question. Yeah. So if with the perfect scenario, you do not want the Krauss span to be all matrices, right? So doesn't that connect to the channel, to the requirement that the channel have multiple fixed points, the noise channel?
Yeah, I haven't think about that question. So
I think there's a definite, like if the Krauss operators form an algebra that's equal to the algebra of matrices on your Hilbert space, then the channel has a unique fixed point. And I think the converse is true, that it needs to not span the algebra, so that you have multiple sectors. Sort of your algebra will be like block diagonal in the space of matrices, and then you can't connect the blocks, and so each block has to have its own sort of fixed point. So maybe this implies that basically
I think that may be true. So maybe there is some connection between this crossband and the fixed point. Yeah. So yeah, it'd be interesting to look. Yeah. Okay. So so just to summarize, the QC protocol goes like this. We have a bunch of probes and a bunch of ancillars. And the first step is we do some encoding of this probe and ancillar pairs. And basically after the first level encoding, then everything becomes a qubit. So we have a bunch of logical qubits. And in the case where Hamiltonian is not inside the crossband, we would have a noiseless logical qubit. But in the case where the Hamiltonian is inside the span, we would have a noisy logical qubit. So and then we would entangle this logical qubit in different ways based on the assumption. So when Hamiltonian is not in the crossband, we are going to entangle this logical qubit using the GHD state. When the Hamiltonian is inside the span, we are going to entangle this whole thing using the logical spin squeeze state. And then in both cases, one can achieve the optimal HL coefficient or the SQL coefficient. So in the first case, the Heisenberg limit is recovered and the optimal HL coefficient is achievable. And in the second case, the optimal SQL coefficient is achievable for both parallel and sequential strategies. So okay, to conclude, we have shown that the structure of the noise and the Hamiltonian determines the estimation precision limit in quantum metrology. And we also shown that the quantum error correction is powerful. Basically, we can use that to recover the Heisenberg limit, and we can also use that to achieve the optimal HL and SQL coefficient. And there are some generalization of what I've talked about here. So one thing is ancilla free protocol. So basically, instead of having this ancilla there, we would also want ancilla free protocols because that's more like experimental friendly. And we've discovered some conditions under which ancilla free protocol is possible, and that is discussed in this paper. And we also consider the multi-parameter case, where we have some Hamiltonian estimation on the Markovian noise, and that's discussed in this paper. And we've also shown that there is some deep connection between covariant quantum error correction with this quantum channel estimation in this paper here. So, and there are some future directions. One is that we don't actually know what is the power of parallel strategy and sequential strategies when the Heisenberg limit is achievable, because we only know what is optimal HL coefficient for the parallel strategy, but we don't know if in the sequential strategy we would have the same optimal coefficient. And another direction is to just develop the general multi-parameter estimation theory for the general quantum channels, because like in this paper we only solve it in this special case, but like in general, no one knows what's going to happen. And also we could consider what happens if there's noise in this error correction part. So yeah, so that's more complicated. Okay, and so finally I'd like to thank my collaborators and especially my advisor Liang Zhang, and thank you all for listening.